Hello, all. Greetings from India and Dubai. Me and my teammate Tejas will give our presentation for the Big Data for Health project, uh, wherein we are re-implementing the FarSight paper, where we are trying to model long-term diseases using unstructured clinical nursing notes. So, what did FarSight do? Before we go into what we re-implemented and how we extended the paper with some interesting ideas. FarSight basically uh, proposed an aggregation mechanism where we can use unstructured nursing notes and predict ICD-9 diagnostic codes. So they proposed a very nice framework where we can just take the nursing notes from the Mimic 3 dataset and do some form of data pre-processing and cleaning, and basically generate long uh, long output tensor where uh, a single admission of a patient can you can predict what possible outcomes can what possible disease out ICD-9 outcomes can happen in the future. So what we recognized when we read the FarSight paper was that FarSight paper is definitely quite old since it's from 2020, and the fact that they used static embeddings like bag of words and talk to vec, and then they also had some feature engineering pipelines on top of it where they did some form of feature engineering. So what we did was we tried to after the re-implementation we tried to extend the paper by using transformer based embeddings. So we picked up a BERT model called BioBERT, bioclinical BERT. So bioclinical BERT is a model that's pre-trained, fine-tuned on another pre-trained model called BioBERT, which is a domain-specific version of BERT, and it is pre-trained on a huge corpus of the Mimic 3 nodes. So not only the nursing nodes, but all the possible nodes in the Mimic 3 dataset. So we hypothesize that using a model like bioclinical BERT would be able to capture more nuanced semantics from the text, and that would definitely save a lot of time. If we had That would save a lot of time of training and computing the static embeddings from scratch, since you can do some form of a transfer learning approach. And the second idea we had was that we would make a mixture of experts model. So what we did was, since Farsight had a lot of different uh, model implementations in their paper, so we thought that we could maybe uh, we could basically use all the different type of models and create a mixture of expert model. And the idea behind that was that there seems to be a lot of variability in the data based on the incoming patient. So we would expect that each model, based on its inductive biases, learns different things from the input data. Like there would be definitely differences between uh, MLP and something like a convect. So we thought that we would use these two. We would use this mixture of experts, and we could also infer that based on the incoming note, which uh, which model is doing the best or which model is being weighted the highest. So next, I give it to my team partner Tejas to explain this in detail.
Okay, so here we present a detailed comparison between the two types of embeddings we just talked about, the static embeddings and the contextual embeddings. NMFTW, that is non-matrix factorization, term weighted using the semantic coherence, is actually using the static embeddings. And what we proposed, the is using the biclinical BERT, which are the contextual embeddings. So the static embeddings have captured the rich information in the unstructured clinical notes, which might be specific to patient. As seen, the NMFTW model is performing slightly better, or we can say it's comparable to the performance we have presented in our paper using the bioclinical BERT. It can also be understand that the bioclinical BERT model, which is actually a pre-trained model and it is a domain-specific one, this might have missed some patient-specific information which has been captured by the static embeddings. However, there is a very good trade-off that can be presented between these two kind of models. The NMFTW with SC was originally trained from scratch on top of all the data, where the number of clinical nodes was in some range of millions. So with over there, the training time was pretty high. The consumption, the resource consumption for getting those embeddings was also high. However, what we have proposed, where we have used a pre-trained model, this one has utilized the power of transfer learning, and then we also have lower resource consumption and then lower resource time. So with this trade-off, we kind of prove that using this pre-trained model, where we have saved a lot of resources and then time, though our model performance is still comparable with what we have achieved from a lot of feature engineering and the meticulous training that was done by NMFTW with SC. Next, we will talk about the mixture of models. So as we already explained, that we tried to set up a mixture of model where we hypothesize that different kind of models have the capability to respond to different target classes, which we have in this particular data set. With this mixture of models, in the results, we see that this model performs better for both the kind of embeddings we consider, and the performance is still comparable with the NMFTW with SC. So this model tries to identify the expert models based on the target classes which we have. So for MOE on mean embeddings, we had an observation that bi-LSTM is a specialist for around 60% of ICD-9 classification tasks, which was followed by Conv LSTM and ConvNet, which was taking into account the remaining 40%. The mean embeddings here provide a better representation of clinical information. And then bi-LSTM considers both past and future dependencies, thus combining the best of both. For mixture of expert on the class embeddings, our observation is that ConvNet is a specialist for around 50% of ICD-9 classification, and followed by bi-LSTM and Conv LSTM for the another 50%. And then this class embeddings provide a summarized representation of clinical node. And the ConvNet's ability to capture local patterns proves most effective here. So with this MOE, we kind of proved that in the complex tasks where we have different target classes, it's often better that we can combine the capabilities of various models, and then we just let the a gating network decide the request should be routed to which specialist. In fact, for this setup, we put in a gateway network which was trained to route the request to various models. And then the parameters of the model were freezed. They were not getting trained while the training of the gateway network. So with that, we just close our presentation. Thank you.
Thank you. Thank you.